It was. Okay, I think we all need to acknowledge that we're being recorded.
Sure. Thank you.
Okay, let's just one more minute. I just want to make sure that, and we only have 3 talks, so I think it's okay. Just want to make sure we have enough time for people to come over. Okay. If not, it'll be a very intimate setting, which is great. Okay, yep, as I thought, we're getting more people. Okay. One more minute. Okay. In the interest of time and keeping with the schedule, we're going to go ahead and get started. Welcome, everybody. This is the Mining Software Repositories session 7. And in this session, we actually have a small number of papers. We have 3 papers in this session. My name is Grace Lewis, and I work at the Carnegie Mellon Software Engineering Institute, and I'll be chairing this session for today. Our student volunteer is Esther Mukoya, and she will be helping me keep track of any problems that you have, but also making sure that all the questions that are posed are answered. So to get us started today, we have the first talk in this session is Dependency Smells in JavaScript Projects, and our presenter is Abbas Javan Jafari from Concordia University in Canada. Please go ahead and get started, Abbas.
Hi, everyone. I'm here to present our work on dependency smells in JavaScript. I'm Abbas, and in this work, I had the pleasure of working alongside my colleagues, Diego Elias Costa, Rabe Abdul Karim, Emad Shahab, and Nicolaus Santales. Our work is focused on the problem of dependency management, and a common dilemma in dependency management is the question of whether or not we should update or not update our dependencies. On the one hand, we want to constantly update and receive the newest fixes and features, but on the other hand, updating too often can cause stability problems due to incompatible version releases. Semantic versioning was proposed as a standard to address this dilemma. This would allow the maintainers of our dependencies to communicate the extent of backwards compatibility for newer versions of their packages. The way we would use a semantic versioning compliant update strategy is we would allow automatic updates to new backwards compatible releases for our dependencies. That means we would automatically accept new patch releases and minor releases, but we would not automatically fetch the new major releases because they are backwards incompatible. The problem, however, is that this is not always followed in practice, and developers often opt for alternatives, which could be problematic. So what is a dependency smell? Dependency smells, as we define it, are recurring violations of dependency management guidelines that can have negative consequences on the project and or the ecosystem. In our study, we cataloged 7 dependency smells. In this presentation, I'm just going to focus on the first 4. Let's start off with an example of what a dependency smell is. Here we have a package.json file, which is where we specify our dependencies in NPM. As you can see here, the developer has pinned the jQuery dependency to version 3.4.1. This is an example of a pinned dependency smell because in this case, we will not be receiving any sort of automatic updates or fixes. If we go further down, we see an example of an URL dependency smell. Here, the developer has decided to circumvent NPM entirely and use an external link to fetch their dependency. This external link, of course, can include malicious files or become inaccessible at any time. But are dependency smells even harmful? we conducted a survey of 41 practitioners, and we asked them about the pros and cons of different dependency approaches. And for dependency smells, they had a range of problems, ranging from bugs and vulnerabilities, dependency breakage, and even breaking changes. In general, practitioners confirm that these dependency smells are harmful and their use is often unjustified. Next, we want to see if these smells are even prevalent enough for us to worry, because if they're harmful but they don't really exist, we don't have anything to worry about. So we conducted an empirical study of 1,100 JavaScript projects, and we found that in fact, yes, dependency smells do occur to a large degree in JavaScript projects. Although, as you can see here, not all smells occur to the same degree. We also did a project-wise analysis, and we found that 96% of the projects in our dataset had at least one instance of a dependency smell. We also wanted to look at their evolution behavior over time, and we actually plotted their accumulation. As you can see here, for the majority of the smells in our catalog, we actually have an accumulation of smells over time, and there's an upwards trend. And finally, we wanted to see why dependency smells occur, because if we know they are harmful and we know they are prevalent, why do they even exist? So going back to the 1,100 projects that we looked at in our empirical analysis, we actually emailed the developers of the commits that introduced the dependency smells to the project. And we asked them why they opted to use this approach. And we got a range of responses that we actually cataloged and categorized. But here we have some examples. So for example, for the pinned dependency smell, one of the respondents said, a newer version of this particular package broke my test in obscure ways. So basically, they had an issue with breaking changes, and they had no choice but to pin that dependency smell. For the URL dependency smell, one of the respondents mentioned how they needed a fix that was available on the GitHub repository, but it was not yet published in NPM. So they had to actually link directly to the GitHub repository. The key takeaway here is dependency smells occur as a response to dependency misbehavior or shortcomings of the NPM ecosystem. Thank you all for listening. I look forward to your feedback.
Thank you very much. This is very, very interesting work. But just to remind everybody that we're going to do all the presentations first. So thank you. Questions are already starting to come in, but we're going to save them till the end. We're going to do questions in one of two ways. If you would like me to ask the questions, I'm more than happy. Just write down your question. I'm more than happy to convey it for you. If you would like to ask the question yourself, just say I have a question for Abbas or I have a question for Aish. And we'll do it that way, but we'll definitely save them for later. So thank you very much. Our second speaker is Aish Sivaraman, who is going to talk about mining idioms in the wild, and she is from UCLA. Please go ahead.
Thank you. So thanks everyone for attending the talk. I'm Aishwarya, I'm a UCLA PhD student, and today I'm excited to share with you our work on mining idioms in the wild with my collaborators from Meta. So the main motivation behind our work is that developers often write idiomatic code. So for example, in this case, we want to process data in a vector, and a common pattern is to loop over the elements and compute on it. So this is not an isolated example. In fact, such examples occur all over the code base. And usually an idiomatic imperative code fragment has a single semantic purpose, which can probably be replaced by a more functional construct like an API. In fact, for these particular examples, we can replace all of these imperative code with a map API. Now that we have seen these example patterns, let's see how an ideal idiom mining engine would work. So the mining engine would take as input a set of code, and it would output an idiomatic code pattern that recurs. This pattern can be syntactic or semantic, but the main observation here is that it can be constructed from a set of nodes that typically occur in a sequence. Before we get into the design of such a miner, why do these imperative idioms continue to linger in code? So this could be because of several reasons. First, it could be because developers are unaware of the API that replaces imperative code, or maybe a new API construct is introduced, but imperative locations have not been consistently updated across the code base. Or maybe an API that would simplify this idiomatic pattern has not yet been included in the language at all. Identifying such idiomatic patterns can help in identifying missed refactoring opportunities, which is the main use case of our work. And further, if you replace this idiomatic imperative code with their API calls, it can help in maintainability and comprehensibility of the code base. Moreover, if we have such an approach that identifies idiomatic code location, it could serve as an educational tool for developers when they submit their code to an IDE or when they submit a pull request. Additionally, the identification can also help language developers in developing new language constructs. For mining good patterns, we need a good representation. On the one end of the spectrum, we have abstract syntax trees, which are very easy to compute, but they produce sparse idioms. And because they produce purely syntactic idioms, they are oblivious to semantics, and therefore they tend to capture shallow idioms. When looking for better tree representation, on the other end, we have program dependence graph, which are very good at identifying high-level concepts, but then they are computationally expensive and not scalable to large repositories. In fact, Alamanis et al. Proposed semantic loop idiom mining using which capture high-level concepts, but they suffer from several limitations. Specifically, to identify data flow patterns, they use an expensive data flow procedure, which is a computation that we don't want to do with like large repositories. Second, the lexical ordering of variables lead to different patterns. And finally, different number of read or write statements lead to different patterns. To overcome these, we propose J0, an approach that works around these practical complexities of prior work on idiom mining. We add semantic data flow information as an extension to the AST. And these augmented trees are generated leveraging an inexpensive and cheap data flow analysis. Our key insight is that semantic patterns can be captured as canonical data flow trees. Finally, we reuse Bayesian learning techniques proposed in prior work to mine idiomatic patterns. The figure here provides an overview of our approach. We first construct data flow augmented trees from a code corpus, use existing unsupervised learning approaches to mine idiomatic code patterns. Moving on to evaluation, in this talk, I will be going over our first experiment where we measure the accuracy of our proposed approach in identifying known refactoring opportunities based on a manually constructed validation set. For this evaluation, we compare against Haggis, which is an AST-based idiom mining approach proposed by Alamanis et al. Haggis does not have the data flow augmentation, but it is otherwise identical to J0. We compare recall and F1 scores and precision. On average, J0's F1 score is 7.1 times better than that of Haggis on all the APIs. This shows the effectiveness of the proposed static analysis-based tree representation. The differences between the APIs also reflect how well this new tree representation can identify diverse patterns. For other experiments, we refer you to the paper. So in summary, we've come up with a new data flow substituted AST tree representation that is effective in capturing semantic idioms. We also conducted an initial user study with 20 developers who confirmed the usefulness of potentially new refactoring locations. Thanks.
Thank you very much. Very, very interesting work. This brings us to our third and final presentation in this session. It is titled The Impact of Flaky Tests on Historical Test Prioritization on Chrome. And our speaker is Emad Falazadeh from the Concordia University as well in Canada.
Thank you. Hello, everybody. My name is Emad, and I will present you with the impact of Flaky test on historical test prioritization on Chrome, the work I did with my supervisor, Dr. Leaky. So in this study, we wanted to understand how test prioritization algorithms perform on large-scale projects like Chrome and in the presence of flakiness. So what we did was that we examined 276 million test runs from Chrome, which we captured from the Chrome website. We captured all of these test results from the Chrome website, and we re-examined prior historical test prioritization algorithms like Kim Importer and Album on this big data set. We published the replication package and data in the following link. And I guess the data is so valuable is because it's one of the rare data set that consists of the test results from a large-scale project with And we also included the flaky flags that the Chrome website has for the test results. And the gap in the previous studies. Actually, the problem was that in the previous studies, only fewer previous studies considered flaky failures. Album et al. Didn't differentiate flaky test on Google dataset. Peng et al. Studied flaky test on a tiny dataset with only 252 Travis CI jobs. And the other problem is that flaky tests might be exaggerated by many of these studies by the way they are trying to identify flaky tests. For example, Al-Shamari et al. Found 67% of tests as flaky by rerunning tests 1,000 times. But we only found 0.03% of tests as flaky in Chrome, and they rerun failures 3 to 10 times. So the huge difference in the percentage of flaky tests, we guess that it's because of the way in the academic works and industry, they try to identify flaky failures. Actually, in industry, they only rerun a test when it's a failure, and they only rerun it up to 10 times, a couple of times. The other important point that we have to mention is that flaky tests on Chrome do not stop the build. As you can see in this build, we have 195 flaky tests, flaky failures, and the final result is succeeded. So the flaky tests do not stop the build from being integrated. The idea behind most of the historical test prioritization algorithms is that tests that fail in the past will fail in the future. So we consider flaky tests as a true failure, like many of the previous studies. And this is the result of running Kim Porter and album algorithm on the Chrome dataset. This is the gained hour against no prioritization. As you can see, the distribution is uneven, but for both of them, almost 25% of the failures are delayed. And but for the Chrome, the median gained hour is more than 2.5 hours, and for album is more than 5 hours. So the result is pretty good for both algorithms. But when we consider the fact that flaky tests do not stop the build from being integrated, and we only considered true failures in our simulation, we see that the result is detrimented significantly. For the album, the median goes to 0, and for Kim and Porter, the median goes to half an hour of the gain. So we go a step further to see what's the reason behind this poor result when we consider only true failures. And we saw that out of 100,000 failures, there are only 99.58% of tests as flaky failures, and the minority of tests, 0.41% of tests, are true failures. So the majority of failures are actually flaky failures. And to understand how repetitive these failures are, we use this figure, which is a Lorentz plot showing how concentrated these failures are. And we see that for the flaky failures, 20% of flaky tests are responsible for 90% of flaky failures. And this means that the minority of flaky tests are responsible for the majority of flaky failures. And so they are a minority of flaky tests are so repetitive in the Chrome. But that's not the case for the true failures, since the distribution, since it is more evenly distributed for the true failures. So in conclusion, for history-based test prioritization algorithms, we can see that these kind of algorithms do not work when there are few repetitive failures. But the problem is repetitiveness is the nature of flaky failures, but not true failures. So these algorithms perform poorly when we only consider the true failures. Thank you for joining me. You can join us you can contact us with the following emails, and I will be happy to answer your questions.
Thank you very much. Really, really good talks in this session. Very good. So let me start. You have one question from Aish. It's for Abbas. Is the accumulation of smells over time per project, or is it across project?
Yes. So it's a cross project, but of course it is normalized because we're looking at the history of 1100 projects, and not all of these are added to the data at the same time. They are created at different times. So the numbers you saw is actually normalized by the number of projects at each month, because we did like a monthly analysis for a period of 5 years. And the way we did it is we first plotted the number of instances where people added a smell, and also the number of instances where people fixed a smell, and we kind of plotted the difference and then normalized their difference to visualize the accumulation.
Does that answer your question? Nice. Okay, perfect. I am not seeing any questions, so I have questions for always prepared for each of you. So let me start with Abbas. So one of the frustrations that I have had in doing research related to mining software repositories is that not all projects on GitHub are equal. In fact, a lot of GitHub projects tend to be, toy projects, demos, like not what I would call solid, like engineering projects. So I was wondering if you well, first of all, like, if it was that your experience as well, how did you overcome that? And I'm hoping that maybe we can create a larger discussion with a larger group as to those of you that are doing research in MSR and working with GitHub. How do you overcome these challenges of the variety of problems in GitHub, and also how can you get results to generalize when especially when a lot of those projects may not be representative of, I don't know if the word is reality. I mean, I know it's reality, but I think you know what I mean. In practice, I guess, is a better term. So please go ahead, Abbas, and we can start the discussion.
Yeah, that is absolutely the case. We had a lot of projects on our data set. I mean, we had the obvious, like forks, something you got to watch out for. There's a lot of projects are forks of different other projects. So that's something that we obviously removed. And we did have a bunch of criteria. So one thing that we did, and I'm actually looking at the paper to just make sure we had the numbers right, but we looked at projects that had a minimum of 10 contributing authors and a minimum of 10 commits in the past 6 months. Now, the reason we did this is it's really quite common to look at popularity, and we didn't believe that to be a good metric. I mean, just because something is popular does not mean it's representative of what's actually happening in the
True.
ecosystem. But we did need projects to be active. We did need projects to have an active, commits and have active authors, because we actually wanted to use this data for our analysis. So we try to just keep our criteria to the minimum to kind of have a combination of smaller and larger projects, like less popular, more popular. As long as they were active, as long as they were not forks, we decided to keep them in our data set.
Okay. Actually, you have another question. This question is from Akshay. He says, question for Abbas. Do you have any insights as to why pin dependency smells are significantly more common than other dependencies?
Absolutely. So we asked about the reasoning for all of the different smells, and one thing that is that really stood out for pin dependency smells was breaking changes. And if you actually look at the research, especially on package managers and ecosystems such as NPM, NPM prefers for people to have breaking changes, basically, because it's more about like having the latest and greatest features. There's not a lot of control on what people publish, like in contrast to like ecosystem like Eclipse, where there's like a centralized core, and people are like kind of looking through and making sure nothing is breaking. And npm is mostly about just trying the newest features, and breaking changes are extremely common in npm. And one of the ways you would combat that is using pin dependencies. Now, npm does have a better alternative, I would say. Well, it's a bit more complicated, but npm does have a package lock, so you can actually kind of have both your main dependency file, which can be updated, but also have a log file, which is automatically generated, which would actually give you like the exact version and pin the exact versioning for your entire dependency tree. But yeah, pinning is common because especially when you're talking about industry projects, it's making sure the code is stable is in many ways prioritized higher than making sure you have the latest fixes and the latest updates. So it actually does make a lot of sense. Does that answer your question?
Yeah, pretty much. Thanks.
Wonderful, thank you. Okay, I'm not seeing any other questions, so I'll go ahead with the ones that I have here. And please keep on bringing your questions. We have a lot of time for discussion. This was a really interesting session. Ahmad, I have a question for you. One of the conclusions of your work is that the majority of failures are flaky failures. Do you think this result is specific to Google, to their processes, to not Google, I'm sorry, to Chrome, Chrome, or the processes that the development processes that they use, or would you expect this to generalize to other organizations and other types of products?
I guess that we can, to some extent, generalize this idea, and that is also an eye-opening study, because the other data sets and the other studies has to consider their flaky failures and to see whether these failures are true failures or flaky failures. Because in the previous studies, there's not a kind of separation between these two kind of failures. For example, we have a public data set from Elbum, but there's not a kind of separation that the result is only pass and fail. But that's not the case for Chrome. For Chrome, we have very complex outcomes. They have immediate results like pass and fail, and then we have final outcome like the flaky result or unexpected result or expected result. But I guess that if many other works actually revisit their studies, they would see a lot of their failures as being flaky failures. Because as we can see in Chrome, as a representative of a large-scale project, the majority of repetitiveness in the failures are because of the flakiness of these failures.
Observation, and as a follow-on, is the expectation of your findings, like looking to the future, and especially because this is a software engineering and practice talk, are you recommending people to change the processes? Like, what is the recommendation for practice that is coming out of your study?
Sure. One of the important thing that we have to mention, that we have some important conclusion from this study. The first one is that many of the previous studies just consider very small data sets and small projects, which is not the case, and which should not be used for the test optimization problem, because when you have like 2 builds in just one day, it's not important how do you prioritize or optimize these tests. First of all is the data set you're using. And then the other point is that the way people identifying flaky failures, in many studies we've seen that actually they rerun a test thousands of times to see if they see any other result. For example, a pass would become a failure. But when you rerun a test thousands of times, you will finally break it. So that is not the case in Chrome. In the industry, they actually rerun a test when only they have a failure, and they only rerun the failure a couple of times. And if it's a pass, then they just move on. So they're not trying to break a test, but in contrast, they're just trying to a test to become a passing test. So
Right.
yeah, that's very important as well.
Okay, thank you very much. So question for Aish, something very similar to what I just asked Emad. So again, software engineering and practice paper, based on the results of your findings and what you've developed. So what is your recommendation for practice or for the practice? Aish, we can't hear you.
So for like say large repositories, if you want to have like semantic information added to your any representation that you come up with, I think for us it was really hard to do testing based or like slicing based analysis, like something that is more expensive. So we ended up just doing like these really ad hoc way of constructing semantic information. Like for example, we added types based on just looking at syntax. Like if you had like a syntax that had vector, then we would say it's a collection. Otherwise, it remains a primitive by default. So I would say that in practice, if you have a large repository, like you need to construct these information using inexpensive methods. And that was one thing that really helped us, because when we tried using, let's say, testing based methods, right? Like not all parts of the repositories had tests, and then it was not covering the whole code base fully. And also maybe tests for one part of the code base was not relevant for the other. Like we couldn't get it to run together and so on. So that was the finding for us. And we thought method of adding, like say, ad hoc semantic information worked quite well. In fact, we started it off thinking, oh, maybe it will not be as good as the program dependence graph, but it turns out that this approximation is actually quite nice.
Okay, so I saw that some folks on your some of the co-authors on your paper are from Facebook. Did you do this while at Facebook with Facebook data? Like, what was the Facebook relationship in this project?
So I did it while I was an intern at Facebook. So I spent a couple of months with them. Yeah.
Well, that's a good internship. That's pretty cool.
Yeah, I thought so too.
Okay. So I'm still waiting for your question, so I'll keep asking questions. So let me ask a meta question, open not only to the authors, but also to anyone who is attending, who also does, for example, research in this area. So obviously, mining software repositories, it's been a field. I mean, it's existed for a long time. In fact, there's it has a conference of its own, right? The MSR conference, and I'm sure I've seen a lot of you at that conference as well. But I think that there has, and again, and AI and machine learning have also existed for a long time, but it's now that, it's become super, super, super popular, and you see that a lot more MSR type papers that are using AI and machine learning techniques. So a question for the authors first, but again, anybody chime in. This is just to create discussion. Like, do you think the introduction of AI and ML techniques, or I would say not introduction, but like the popularity, is affecting the way that you approach your research, will affect the way that you approach your research? Do you think it's oversold? We've been doing this for years. We don't need that stuff. Like, what is your opinion on how AI and machine learning are changing and will change the field of mining software repositories? And let me start with Aish, because I'm looking at you right now. You're like in the big screen.
So I think like specifically for mining software repositories, it's all about finding patterns. So I feel like as we find new ways to identify patterns, it's definitely going to influence the kind of results that we get. I think like earlier we used to kind of do like maybe k-nearest neighbors. That was like the easiest thing to find patterns together. And then things got more sophisticated. And I think now we have these RNN or graph neural networks. And I feel like a lot of good pattern detection has come by including AI and machine learning into the problem, because maybe some patterns are not just like easily detectable using heuristics. So that's what we used to do like a while ago, maybe a decade or two ago. But then I guess if you didn't want to construct heuristics, or if you wanted like a systematic way to construct heuristics, I feel like using these AI and machine learning techniques will give you that kind of systematic way. I'm not sure how rigorous it is, right, to say that it is systematic, but at least you kind of have like a huge data set and then you're not overfitting and so on. So I feel like it is helping detect good pattern. So I would say it's a good influence, at least for mining software repositories.
Okay, Abbas, what are your thoughts?
Definitely looked into using machine learning techniques in my own research. I really focus on empirical research. So for me, it's mostly about having descriptive models. So not all models, even though they might be super performant, like the deep learning stuff is really popular right now, but it's not always the best from like a research
Mhm.
standpoint, because you want to know why something works, not just that something works, right? So yeah, I think there's definitely going to be some influence, maybe not at the same pace as the industry or in the same type of models that people are using, but definitely, yeah, especially when you're dealing with a lot of data and you're trying to like uncover relationships. I'm already using it in my follow-up work, actually.
Can you talk about that follow-up work?
I can. So it's actually a follow-up to my dependency work, because one thing that we realized in this study was that a lot of the problems people are having is not because they don't know or they're not aware of the fact that their techniques are problematic, but it's that they are kind of put in a predicament and they don't have much of a choice, because the package they're using is behaving in a way uh, that would kind of force them to opt for these
Mhm.
alternative approaches.
Right.
So one thing that I'm working on right now is trying to find a relationship between uh, the characteristics of those packages and how people use them. So, because and that's something that hasn't been done before. We haven't looked at why people depend on a package in a certain way. Because one thing that we found was there's definitely a difference. Some packages are used in a very semantic versioning compliant kind of way,
Mhm.
which maybe we could see them as an indicator of trust. And some packages, when people use them, they're definitely more conservative in how much freedom they want to give that package to automatically update, which could
Right.
maybe be an indicator of mistrust. We want to be careful about that. So I'm looking at how like different characteristics of those packages influence, and maybe if we can like find a way to model or maybe even predict how people will use a package based on the package itself.
Mhm. Yeah, super interesting. Thank you. Emma, your thoughts?
Sure. As someone who had been working on machine learning in my master's, and that
Mhm.
it was a different area, like doing some market price predictions,
Mhm.
etc. But uh, I guess it is very important for all of the areas that using machine learning that they have to understand the underlying data and how these machine learning can solve their problems. In some cases, they're using machine learning too much,
Mhm.
and they don't understand how it is going to predict and how it's going to help them with that data or the prediction. Um, for example, in the market, I remember that if I try to use the best and more complex models of the neural network and fuzzy and kind of
Mhm.
things, but the point was the nature of market was so unpredictable that uh, by using only the prices and the indicators as the input of the data, you couldn't just predict the market, because there's so much of other things like the events and other things that are in the market. So
Mhm.
I guess it's in the articles, in the papers, we have like for the Facebook and Google, there are some test selection techniques they're using by machine learning. For sure, the machine learning is so useful, but we have to
Mhm.
understand the underlying data and how we are going to use it properly.
Mhm. Yeah. So it's, yeah, I think I heard a common message across the three of you, which is, yeah, they're useful, but use them carefully because they might not be the solution to all your problems. Anybody from the audience interested in chiming in on this comment or this question? Very quiet crowd today.
To add something.
Actually,
Yeah. So
go ahead.
Yes. So I think like introducing machine learning techniques is great, but we need to be careful of the complexity they add. So I think they add complexity in 2 dimensions. So firstly, testing becomes really hard because if the machine learning system, say, doesn't give an output or let's say a pattern that you expect, you don't know if it's a bug in your code or in the model or in the training data, or it's really hard to debug. And secondly, now if you have other other developers on the same projects, now they not only need to be experts in maybe software analysis or static analysis or whatever you're using, they also need to be experts in machine learning. So I think you need to be careful about that, and the sort of increased complexity should be worth the the improved results.
The added value. Yeah.
Yes, the added value, right?
Yeah, perfect. Thank you. That's a good observation. Tushar, you want to say something?
Right. Well, not probably on this topic, but you were having a discussion earlier with another. Sorry for my throat. Another interesting topic, which you were mentioning, that how to select repositories from a vast number of repositories that we have on GitHub, and that's actually, I think, all the MSR researchers face this problem, because this is we can't obviously analyze all the, I don't know, maybe more than 30 million repositories. So we need to have some sort of a sample, and sampling is actually a very important problem. So and representative is, when we say it should be representative, that's often subjective. It depends a lot on what we are actually studying. However, there are some guidelines, and that typically MSR researchers follow. For example, if some people use repo repos, this is one of the ways to measure the different aspects of a repository, like whether it is documented well, or whether it has test cases included or not, or whether it has a license file or not, or many other different aspects. So that is one big database that some people refer to. Another one is GHTorrent. Maybe most of you probably know about that, and it also won MIP award and MSR. So that also another thing, that some people use that database as a base to run some sort of a queries and select a subset of the repositories. If you are also looking for quality related aspect, then you can also use Q-score to filter out the very toy projects or small projects, or where the repositories are low quality or something like that. So these are some thoughts that just came, and I thought it worth sharing. And I see many senior researchers here, so maybe they can also share their thoughts for the good of the rest of the people.
Yeah, that's very good input, especially like you said, if we have a junior researcher here that are trying to get into this area. Those are all very good pointers. I have used GHTorrent in the past successfully, so I definitely would recommend that. Good, nice reference, Abbas. There is a question for Aish. It comes from Malinda. Aish, a small question to you. I am curious to learn about the nature of the code change instances of each pattern. Do you think that all the code change instances per pattern detected by the tool are semantically equivalent?
So to a certain extent, yes. So we did do some manual analysis, and also we conducted a user study to ask the user. So let's say that if I learn from like a data set of map APIs, and then we detected a pattern and further identified few instances, we would show that to the developer and ask, oh, do you think this particular imperative code can be replaced with a map API? And then I think for the top 2, 3, like we showed top K, I'm not exactly sure about how much K it is, but when we showed the top K results, they were able to confirm that, yes, this indeed is a useful refactoring location. So, but as with the patterns, I'm pretty sure that if we expand it to other APIs, we would have to first check and see in a validation data set whether it is true. But at least for the ones that we had done validation for the 4 APIs, yeah, they are semantically equivalent.
Okay. Does this answer your question? I don't know if Marlene is still around. Yes, she is. Okay, perfect. Thank you very much. Okay, any other questions or any other discussion topics? Okay, so if we have no other discussion topics, thank you again to the 3 speakers. These were 3 very interesting topics in a topic that is dear to my heart. Also, a very big thank you to Esther Mukoya, who helped us as student volunteer that helped us. She posted in the chat session. She posted some of the links to the preprints for some of the talks today. Thank you very much. Continue doing good work in this area, and hope to see some of you at ICSE in Pittsburgh, and if not, maybe next year in Melbourne. Take care.